Hello and welcome back to Compiler Programming. Today I was sitting down and profiling the parsing and compilation of this test file that I have. This is something I saw from Andrew Kelly, the creator of Zig. Basically, it's a simple file that has 1 million print calls. So if you look in the corner here, you'll see that we are at the line 1,016,000 and some characters. While this is not particularly representative of a program, it's a nice test because it allows you to sort of focus and see what is the theoretical maximum performance that you can get out of this. So let's actually run the profile on that. I have it set up here as a test that is usually disabled because I don't want to wait for it every time. But maybe as we improve performance, I might actually fold it into the main suite. Let's see. Anyhow, so I just run this single test. So here I set up this in the release mode as well. So we are compiling with all the optimizations. Otherwise, the data that I get in the profiling is completely bogus. So let's take a look at what's happening. Okay, so that wasn't too bad. It is 2.5 seconds, something along those lines, but it could definitely be much better. Now we can go in here. First of all, you can see we have a big problem with memory, but that's something we'll actually look into in a second, and you'll see why. First, I want to look at the CPU profile. Okay, so this view, I think, is not always very informative of what's going on, but one thing I noticed, so we are now sorted by the total CPU time that is spent inside the function, and when you have optimizations enabled, this view might be more interesting than the self CPU because with inlining you will not see always correctly what is the self versus total, as you will see in a second. So it says that self time is 4% here in a call function overload, but the total time is 17%. And this is a bit suspicious. So if we click on here, and maybe let me okay, that gives us a bit more space here. So if we make this one bigger and maybe make this one bigger, we can look at the code and it shows sort of the percentage of time of the total program that is spent in this particular function or this particular line. And as you can see, a lot of the lines are not visible. It's because it's an optimized build and those instructions just the compiler cannot map them to what was in the source code always. Just something interesting. I understand why that happens in current production compilers, but I think that at least for now, that should not happen in mass, and when we get to debugging, we should see all of the direct mappings. Right, so there is a bunch of these scope make stuff, so it's something to look into, but it's not what I'm interested in at the moment. The more interesting thing for me is, okay, we have nothing here, nothing here, nothing here. There is some small usage here, but nothing really interesting. And then we get to this 12%. And this is roughly the difference between self time and the total time. But push instruction is not visible anywhere here because it is inlined, and the actual I can even search push instruction. Yeah, it does not have it there. And that's because majority of time here is actually spent in allocating memory. And the way we can see that is if we look at caller callee setup, and we are looking at this call function overload over here, and we are spending time mostly in ensure capacity, which is like array resizing routine, and then this kernel, which is where the memory allocation happens at all, and you have also a bit of a buffer. So these 4 functions account for almost 10% of the total execution time, and this is not cool. Now, why is this happening? Well, there are a few reasons. First one is we just have an array with 1 million elements, which is not great by itself, but additionally, the problem with that array is that each of the elements is very, very large. Let me show you that in reality. So if we go to meta.c, where all the types are defined, and we look at the instruction here, then the largest type would be a combination of these. So this is like 8. I think storage is super gigantic. It is probably 24 bytes. Maybe we can check here, and it will show us better than in calculating it manually. So right, can I hover and will it show me the size of this? No, it will not. Okay, well, back to manual calculation, I guess it is, but just roughly that's 8. Here we probably have another 16 indirects. Yeah, well, I guess this is around 24 bytes. Let's just say 24 for each storage. This is 8, and this is 24 times 8, so that's, times 3, so that's 72, 80 bytes. And then we have this stuff over here, which is 16, that is another 24, and then this is also like 24 bytes. So one instruction that we push is more than 100 bytes, which is really a lot. And as you imagine, if we have 100 bytes per instruction, we have 1 million instructions happening here. Well, here's your 1 gigabyte of memory, or 100, I mean, yeah, it's 100 megabytes, but there is also alignment and extra stuff, so that's a lot of memory. And this is not great. So what can we do about that? Now, one idea I had for a while is to not store the instructions like this, and instead store them as bytes right away. And I think it's time that we try to do that. So we can go into the encoder, and we will copy this function. That is quite a lengthy function. I will eventually merge the copies probably, but for now it is much easier if we don't break the existing code and we just start sort of chipping it one by one. Now, let me first explain what is going on. So let's say that we are inside of, let's say that we have an instruction like this. So this is the sign extended move from the source to some other operand. And when we do push instruction, this stuff is just stored inside of the instructions array in each builder for the function. So whenever we have a function like this, right? So each function like this has a bunch of storage that has instructions array. and each call will be one instruction: call, 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 right, like this. So let's say we have like call, and then usually call is with a label, so some kind of location in memory that we can call. If we have an add, this would be something like rax htx. So we're adding, or we say add rax 42, so we're adding 42 to the register arrayx. And this is what is stored inside of this variant of the instruction. And then when we are encoding, we go through each of the operands and we turn them into bytes. Okay, so what am I trying to do? Instead of storing it as operands, I want to right away store it as bytes. So this will be like 0x, I don't know how it's encoded, but whatever. Let's say AAFF. That's not really how those instructions are encoded, but the point is you just have maybe 42. So you have 2 bytes, or this is 2A. So you have 3 bytes for this instruction, or something like this, which is much more efficient and great. And that works perfectly for instructions where you do not have labels. And if you do have labels, you're in a bit of a trouble. The problem you run into is that you don't know which bytes to put here. So here you have basically like 1, 2, 3, 4 bytes, and you don't know what are these bytes. Maybe like this is more visible. So you have, let's say, C0, I think is the call. And then you have 4 bytes for a label, and you just don't know what they are. And even when we do encoding here, we don't always know. Let me find this. Yeah, so we have like these label patches where we put essentially zeros into those locations, and then we overwrite them later on with the right value. Okay, if that's the case, then this is exactly the plan. We, instead of storing this information over here with arrayx42, we store the bytes right away. And if we need to do patches to labels, we also just store that information. We store that we need to do a patch here. But right now, I just want to work on this eager part of the encoding, because that seems to be the interesting bit that will eventually allow us to reduce the size of the instructions. And word of warning, I will almost certainly not finish this today, because it will involve going through a lot of the code and just painstakingly looking for this push instruction setup and turning it into the eager one, because it's not always going to be possible to do it automatically. Or even if it's possible to do it automatically, it would be more performant and nicer to dispatch common cases myself. Anyhow, that is enough blubbering. Let's get to the point. We can just review this code and look what we need to change for it to do what we want. So this is fine. I guess first of all, the signature will be slightly different, I guess, but we will see. Let's start like this. So the instruction assembly, let's keep it that way. We do the encoding, we go through each of the storages, that is fine. Here everything seems okay as well. I think the big thing will happen when we need to deal with its labels. So let's look at that. We have this bit of code. So if we have a label here, we just create 32-bit value and we set it as a patch target in here. Okay. That is fine. I don't think we will actually need it because I have another mechanism for doing label patches, which is through another type of instruction. So in a sense, instead of just having a list of uniform instructions, I have a list of different ones. You either put bytes or you put this label patch. And then we go through all of them and we resolve them correctly. And you can see that label patch being handled way over here. Yeah, so basically this piece of code is exactly the same as this piece of code. So we probably should be able to not only unify that, but that will also help us implement what I want to do. Okay, let's start with the usage. So maybe we'll start with this code right here. It's also the simplest one because in a sense these two operands, I believe, are almost always registers. Source, storage register, then source, yes. What about adjusted? Yeah. Okay. Source storage, adjusted source. Yeah, I think that is basically one of the easiest ones. We can also look at add. Now let's give it this one. So push instruction, I think it's defined in here somewhere, maybe, or it is in the header. Yeah, so push instruction is actually a macro that writes the source location, and then it also adds the compiler location, and then finally pushes the instruction in here. Okay, that seems fine. What we can do then is create a new thing that will be like define, or let's just make it non-inline, or not a macro, and that would be push eager instruction, or eagerly encoded instruction. Okay, it needs a pointer to array, so array instruction star instructions. And what else does it need? I guess it needs a source range. So source range star source range, and let's just try writing it up, and then we'll see what else we need. So we'll put instructions. Well, we obviously need the instruction itself. Right. something along these lines, I guess. And for now, I will make it do exactly the same thing as the other one was doing. So that's actually not const. We do this adding of the source range like this, and then we push the instruction. Something like this. Does that build? Right, that's a void, that's okay. And we need a star here. Nothing really fancy for now, but I just want to check that we still work. Right, instruction, source range, and it needs to be ampersand, and it needs to be ampersand over here. Okay, that at least builds. Let's try to run the tests. That's actually the wrong test to run. So we need to disable this here, and I also think I want to disable the tokenizer reporting for now, because that's not interesting at the moment. At the moment, we're interested in the correctness of all of these. Okay, so that is working. That is not surprising, because this thing is doing exactly the same thing as the other one was doing. But now we start with the changes. So we go to encoding, and we need to start thinking about how would this look like. Does it need to accept the buffer? No. So that's maybe the first thing that we'll do. So it will return an instruction, and it will do something like this. Instruction result. But we don't need this stuff. We do want this. We can actually even make it so that it... Oh, that's a change I will do later. Result. And now we can start looking at this. So originally it was pushing to the buffer, but that's not what we want to do right now. So instead right now we define push byte, and we will say that here U8 star byte cursor is result bytes, so bytes memory. So we're taking one of these and we're turning it into one of these. This is what the function will do. And once we are done with all of that, hopefully we will be able to just get rid of this instruction variant at all, which will collapse the size of the whole struct because of the whole union, because this is the largest variant that we have. And then I have some plans how to get rid of a lot of this stuff. The encoded byte size will go away by itself if we get rid of the assembly one, because it will then be encoded in this length, right? So this will disappear, and then like these, this one is purely debugging the compiler, this is debugging for user code, and this is also debugging for user code. So technically if you want to build without them, that will be much faster, but even with them I have ideas. Anyhow, back to our stuff. So we do git byte memory. And the reason I want this to be a macro is because I want to make sure that I don't run over the size of it. So this will be something like byte, and then we do the standard do while setup, right? Do while I cannot type today, while 0, and we assert that byte cursor minus is less than 15. Yes, it's less than 15. Can actually do probably something like this, count of memory, because it's a static array, so we actually know the size. And once we are done, we are just saying that star byte cursor is whatever was the byte here, and then byte cursor plus plus. So that just moves the cursor over each individual bytes. Okay, we have this push byte, and we are ready to use it. We don't need the buffer here, so something like this. And that looks good. Now here is a bit more tricky because we essentially need to push 4 bytes, and also the whole setup is sort of incorrect, and we need to fix this. So for now, what I'm gonna do is I'm gonna comment this out and just say panic and to do. This is what is going to happen here. Okay, and with displacement. All right. So, how do I want to do this? Do I want to depend on being little endian system, or I don't? I guess doesn't really matter, but anyway, here we say push byte, and this is okay. With displacement 34, this is what we're gonna do. We're not gonna depend on little endian, but we're also not gonna be very efficient, I guess. Or I don't care. I probably don't. In x86, I can also just do an aligned right. Let's do an aligned right. To do and get rid of this and unaligned rights. So byte cursor. No, then I will not have the bounds checking. Yikes. Okay, whatever. 8 bytes 4 is like this. Mem copy bytes. Here we basically say size of displacement. When we copy to bytes, and that is gonna be displacement, and then size of displacement. So we're basically turning the integer into bytes, and then we say for I is 0, I less than size of displacement, plus plus I, and we just do push byte bytes I. That is how we push 4 bytes. I guess we want to make it another macro over here, and we will just say, well, if I'm making it another macro, then it might be as well just say something like push U32, and here we say byte cursor plus size of U32, and then would be minus equals, and then we do the following, right? What we were doing here. So we have our buffer, U8 bytes, we copy bytes, and then we say source U32 source is source, displacement, that's now source, like this. Maybe I can inline this stuff. Okay, that is no longer necessary. Does it look fine? Let's recheck. So we have bytes, and that needs to be size of source. Yeah, and in here we can do size of source, so that is a bit more correct. And then we walk through each of the bytes and we copy it. I probably made a mistake somewhere, but we will figure it out a bit later. Push U32 displacement. I know that displacement is S32, but here we work directly with bytes, so we don't actually care about the sign of it. Compiler might complain to us about this, but that's not the interesting part. Okay, what is that? Storage tag static. Do we actually get in here? I'm not exactly sure that this is even happens. Does this even happen? Okay. Encoded byte size, fine. That's actually very easy. We just say result so byte cursor minus result memory, and that should give us the size. Next instruction offset. Yeah, this all is necessary for the patches, but we are gonna be doing patches differently anyway, so that doesn't matter. Memories, no, it's yeah, right. And value specified subject, right? That is correct. So here we have encoded byte size, fine, and maybe I should split it. I don't like to have these multiple assignments because they are a bit hard to notice sometimes. Okay, I think we are left. Length is not right. Bytes and bytes. Great, so this is also not supported. That is fine, we will deal with it later, hopefully. Different const qualifiers, what? Right, and conversion from fine, I completely agree. So S64 to U8, something like this. This is not required. And we have a problem with const qualifiers, but that is not an issue at all. Great, well, this is sort of good, and now we can go back to here and try to use this function. So we'll say instruction encoded is, what is it? What did I call it? Eager encode instruction assembly. Do you even need a program? No, you do not. Okay. That is great. Say if instruction tag is instruction tag assembly. When we do instruction encoded is eager encode of instruction Then we need the encoding, and encoding is stored in instruction assembly mnemonic, and then I can look it up in here below somewhere. Where is it? Where is it? Where is it? Where is it? Ah, right. We actually we need to match the encoding first. Right. So that means that we need to get this part out as well. Is it aligned? Okay. So I think this can be extracted like this. Let's verify that that didn't break anything. Well, apparently it did. So okay, let's do it differently. We right away take this out and we say encoding is encoding find or match, and we take this stuff over here. And we would say const instruction, encoding, static, constant instruction encoding. Yes, encoding match. So we are trying to find stuff here. It doesn't hurt to assert that we have the right tag. Something like this. This can be const as well. Okay. And here we just pass on the instruction. Storage count, that's undefined, that's fine. We can do it again because that's very easy. Okay. Unreachable code. Which one exactly? So we go through this. If it should be like that. Let's try that. Okay, so that it still compiles. That is good news, which means, well, actually, it means that we need to let's push it into here. Constructions, just put it here, because otherwise it will have problem with the resolution of names. Okay, encoded, great. Const instruction encoding. Encoding is encoding match instruction, and then we basically pass the encoding. And do we need anything else? It wants a storage count. Fine. We can do storage count as well. Encoded and reference local variable. That's fine. And we just pretend that we use it. And here it complains that we are not returning the result. And what I'm trying to do right now is we will not use this newly created thing because it may not even work. But we still want to go through the function and make sure that it doesn't crash or nothing weird happens, like this kind of stuff. Stack locations must be known beforehand. Right, this is another thing that I didn't mention and something that is a problem. So, what is this stuff? Right. Right. Let me explain. When you have something along these lines, so we say we want to add RSP plus 80, so some value on the stack, we will add RCX to it. Well, the thing is, I'm using stack pointer directly instead of using something like RPP, so which is a frame pointer. So at the time where I encode the instruction, I don't actually know what is the total size of all the things on the stack. So instead of storing this value directly, it is stored in one of these. Let me find where is that. Yeah, so it is one of these. We have a stack value and it says whether it's a local variable, it is a received argument, or it's a like argument for a call, and we just say that. And then there is another piece of code which is in here. Stack area. Maybe it is in here then. Where do I do that stuff? Let's just check. Stack area. Calling convention. Stack area name. No, that's not it. So that's also not it. Okay, now I'm very confused. I guess it is inside calling convention. Stack area. Yeah, right. So basically we go through all of the instructions and we patch in the right offsets for this for the stack size. So we add right offsets here. Now this is a bit awkward because we have patching happening over here, but at the same time the actual code is happening in here, right? So that's not great. How do we deal with this stuff? Now, one thing is that we never have more than one stack argument actually. So what we could do is we could introduce something along the lines of storage star. Do I want it to be a storage? I guess I want to say so the idea here is that, again, if we have like 01, 02, 03, 405, so we have some bytes over here. We should be able to say that these 4 bytes, they are actually stack offset and they should be resolved later. Now, one thing that is sort of not gonna happen in this way is that there is we cannot select the best instruction because there are instructions just for byte operands, and there are instructions for S32 operands. So you will either have something like this, or you have something like this. And obviously 2 bytes are better than 5 bytes. And we will always end up with 5 bytes here, I think. Now, I might be able to work around that, but for now that is probably too complicated to think about it. The point is we need to know at which location in instruction we will actually get the offset in the stack, because it might happen in different order depending on instruction order. So it might be, for example, these 4 bytes, but maybe we have another byte in here, or it's like these 4 bytes, and we need to know exactly where it is happening. There is sort of already similar mechanism for the labels, so it's nothing new, but it is a bit finicky to get right. How do I want to deal with that stuff? Do I want to go into this? Maybe what I will do instead for now, so we can actually make some progress, and I will have some time to think about that, is we will in here, here. Right. In here, we'll do for U32 I is 0, I is less than storage count, n plus plus I. And we would say if storage, or storage, I can actually copy this from here. Yeah, so storage, if a storage tag is storage tag memory, and storage memory location tag is memory location tag stack. That's quite a long line I have over here. Then has stack operands is true. So for now, I'm just going to filter this out. I will say bool has stack operands false, and here let's say if node has stack operands. So what I'm doing here is I'm trying to maintain the working state of the program as much as I can, because it might be very tempting to now dive into this encoding of stack operands and dealing with all these small shifts and offsets, and it's always a nightmare and it takes forever. So instead I want to just keep focus, and if I can get, for example, all the register to register operands encoded, then that's already a big win, and we can sort of move forward from there. And I can continue working on this maybe offline. Okay, let's try again the test. Okay, so at least the encoding now worked now, but I'm still not actually using those encoded bytes. So we don't know if this instruction ended up being actually used. So first thing is I do want to know that we actually do end up in this branch, and apparently we don't, which is a bit annoying, which means that all of the instructions here that I tried to use don't actually have a variant that does not have this stuff. Okay, well, what if I put it into move value where I 100% know that we have register to register copies? For example, temp followers. So this sounds like a perfect opportunity to do this. And let's keep the panicking. Okay, I did not do this correctly. Yeah, they have slightly different signature. So maybe it is worth to change the signature here to do this. Okay, yeah, that is better. And even more so, let's change this all the way in, just so that it is easier to port old code to this code. Right now I'm not worried about efficiency or anything like that. Ampersand and ampersand. Ampersand requires L value. Okay, we are building. Now I expect a panic. Yes, okay, at least once we get there. That's already good. That's already good enough for me to start testing that this works correctly. So now, if we were able to successfully encode this, I'm gonna push this newly encoded instruction instead of the original one. So we push encoded and we return. And that is basically what is happening. Now we just have to hope that this does not explode, which it does. Kind of unfortunate, but we can switch back here to the debug build and try to run this. Okay, so mnemonic is incorrect. That is very weird. Ah, right, I know. I think I know what's going on. In here, I don't actually create the right thing. So here I need to say tag is instruction tag bytes. Then we have to have source range is instruction source range, and we also have compiler source range is compiler source range. Another member of instruction, is it compiler range? What is it called again? Compiler source location. Okay. Sorry about that. Oh, well, let's see if that makes it better. Great. So that is great. Now we can do. Now, the question is, do I continue or is that enough? I think that is enough. We will try to put it in a couple more places in the code where we do know that we are dealing with registers, and that is going to be about that. Okay. Save stack, nope. No. Call register. Well, we, for example, can put it over here. I already forgot what I call this. I call this push eagerly encoded instruction, right? So for example, this code should actually work. And this is static. And let's try to run it. Okay, that is pretty good. Let's look for more assembly stuff. This is unclear. This is, I think here for adding I can actually use it, or for arithmetic operations, because I believe they are always registers, but if they're not, new code will tell us they are. So this is pretty cool. As I said, now what I need to do is deal with registers, but it's just a bunch of byte fiddling here and there. The way it will work is I will introduce here a new thing called like stack patch, and it will just contain probably memory location stack or something like this. And I will, in here, in the calling convention, I will just use that information to patch the right thing. I said this is just very, very fiddly, and you don't want to watch me spend 2 hours on trying to get the offsets exactly right. Cool. That is then what I wanted to do. I know it's a slightly weird video, but the whole point is this is actually gonna help me achieve the goal of trying to push as much work away from the compiler and into outer layers as much as I can, because there is already this inline machine code bytes, and now we are essentially doing the same for, or will be doing the same for all of the instructions. So eventually user land code will be able to interact with it in a pretty nice way, I would say. Okay, that is all for today. If you stayed far, then thank you very much, and hopefully see you next time.